Hello everyone, I am Arie. I am here to present our paper titled Solving Constraint Horn Classes, Modulo Algebraic Data Types and Recursive Functions. This is joint work with my supervisor, Professor Arie Gurfinkel at the University of Waterloo and Professor Sharon Shoham at Tel Aviv. Let's get started. We are interested in automatically verifying imperative programs that manipulate data types like lists or trees or heaps. We have an example of such a program on the left hand side. It has one method main. It takes two arguments, a list and an integer variable that is supposed to capture the length of the list. And in a while loop that runs an arbitrary number of times, we remove elements from the head of the list and we decrease the length variable accordingly. It is asserted that no matter when you exit the loop, the length variable is positive. To verify this program, what we need to do is to come up with an inductive invariant that proves the safety of the program. In this case, the inductive invariant is that the variable I is indeed the length of the list and that I is positive. To automatically come up with this inductive invariant, we encode the program as well as the assertion as a set of constraint horn classes. So constraint horn classes are a set of constraints on an uninterpreted predicate. In this case, the uninterpreted predicate is inv, and the set of constraints ensures that if you come up with an inv that satisfies a set of constraints, you can be sure that your program is safe. In our case, the set of constraint horn classes will contain algebraic data types in order to capture variables like x, which are of type list, and recursive function in order to capture properties of list variables like the length of the list. Now, why is this challenging? Because recursive functions are hard. In general, properties of recursive functions are undecidable. Intuitively, this is because you usually require induction in order to prove properties about recursive functions. For example, to prove that no matter what the list is, its length is positive, you need to have an inductive argument. Now we have two sources of undecidability. One is that solving constraint horn classes over uninterpreted predicates is undecidable usually, and solving recursive functions even without any uninterpreted predicates is undecidable. The usual workaround for this is to encode recursive functions as another set of constraint horn classes. That is, you replace the recursive function small length with an uninterpreted predicate's capital length, and you use the function definition to constrain this uninterpreted predicate. The first contribution of our work is to show that while this process, which we call relationification, preserves the satisfiability of the formula, it does not preserve solutions of the formula. In other words, we do need recursive functions. The second contribution of our work is a procedure to solve constraint horn classes, modulo algebraic data types, and recursive functions. We start off with a set of CHCs that contain both ADTs and RDFs. We relationify RDFs, so we get a set of CHCs, CHC prime, but importantly, we keep the recursive functions. We have the relationified predicates to infer inductive summaries of recursive functions, and since we do keep the original RDFs, we do preserve solutions. Then we developed a IC3 style PDR algorithm called Razor that solves the CHCs by unrolling and abstracting recursive functions whenever they are encountered. This keeps us in a decidable fragment. And we guarantee that if your program is unsafe, we will definitely find a counterexample for it. Thank you for listening, and please catch our full talk on Wednesday, the 19th of January.